Yes, sir.
Okay.
Yes.
Okay, so let me, I will like for the first 10 minutes, I will talk about the motivation, and maybe that motivation of the code optimization belongs to 5G, or the same thing is applicable to 4G LTE as well. Okay. So, okay. So what, how a normal signal in 5G or 4G looks like? Normally we have a window of 1 millisecond. Okay. And we transmit OFDM, so the orthogonal pulses, which are in time they are 1 millisecond long. Okay, so they are like this. There are many of them. Okay, so the normal, the bandwidth looks like this, which is, it can be 5 megahertz, 10 megahertz, 20 megahertz. So for LTE, the maximum that we have is 20 megahertz. For 5G, it can go 200 or 400 megahertz as well. Okay, and uh, this is the time window. Okay, so basically what happens is when you have some data, let's say your phone is, some application is generating some data and you are transmitting it. Okay, so everything happens in that 1 millisecond. So let's say look at how a cell tower is processing this information. Okay, so what exactly happens when a cell tower receives this and how exactly it process. So assume this is cell phone. It has a single antenna and there is a base station here which has multiple antennas. Okay, in this case, let's say two. You get this information here. Okay, so this base station will receive this information. Okay, so basic. Okay, I will keep them separate. They are basically separate. So the first module is channel estimation, which if you don't know, it's okay. Then it equalize the samples. There are other modules before this, which I'm not talking about. I'm only talking about the base band processing. So even like this. Okay, I'll go with the FFT first. So there is FFT here first, then channel estimation, equalization. Okay, so if you don't know about this module, it's okay. You just consider there are some black box, they do some processing. And before these modules, there are other processing as well, which is like converting the continuous signals to digital, this ADC, and then down converter. So you get the passband signal, right? You convert this to baseband, right? There are other processing handled by the hardware, and then after you do this analog to digital converter, then you have them samples. You give the samples to your DSP chip. That chip will be processing those samples. Okay, so for each antenna, you will do Fourier transform to convert them to frequency domain. Then you do some. There are some blocks here. You consider they do some processing like estimating the signal, what exactly was transmitted, kind of. Then there is some module which combine this information. Then you have other heavy processing modules like demodulation. This can be demodulation for QAM, which can be 16 QAM, 64 QAM. In 5G, you may have 256 QAM, or you may have BPSK. There are few more supported modulations, and then the next block is decoder. If you have heard of the decoders in your bachelor's and masters, like some of them are like Turbo, Viterbi. These are mainly in 4G. In 5G, some of them are like LDPC, Polar, and there are two more. Okay, these are mainly in 5G. So this is a very heavy modules, very intense module. Then you do check. It's basically check whether it actually calls CRC, if you know. It basically checks, okay, whether the information that we have received is correct or not. If it is not correct, you just discard it and you give it to the application. Or it's like wherever the information is going, you just give it to the internet, basically in the broadband. So if you look at this, I have these many modules, okay, starting from here to here, okay. My window that I'm operating is this, which is 1 millisecond. So every millisecond, I'm supposed to do this whole processing. And every millisecond, I'm receiving some new information. Okay, even in 5G, this reduced to 0.5, 0.25, or even 0.125. Okay, but we will just talk about 1 millisecond case, which is common for both 4G and 5G. Okay, so if you look at the modules available here, okay, the FFT is a very heavy module. So consider that if you are taking a Fourier transform of 4096 size, that's huge. Okay, the channel estimator equalizer, they are also huge. Another intense module is the decoder. Okay, so there are three modules: FFT, decoder, huge modules. But in this case, since all of you are familiar with Fourier transform, we will be discussing this. Okay, so if you write a Fourier transform, maybe this used to be one of the assignment for the CSP DSP lab, but this time it's not there. If you write a simple, even if you write a fastest Fourier transform code in C language, it will take you for few milliseconds to seconds. Like if you're writing a simple, the fastest algorithm that you know, if you're writing that code and if it is not optimized, it may take like 10 seconds. It may take like 1 second. If you optimize it further, it may take like, let's say 100 milliseconds. Okay, if you put lots of efforts to do this 4096 FFT, let's say you optimize it to 1 millisecond, or let's say further 100 microseconds. Okay, that's like, it's like you work on the code, you keep optimizing it further and further. Okay, but if you look at here, your receiver don't only run one FFT, it runs 4096 FFTs 14 times here. So this particular time window is divided into 14 blocks. Okay, so in 1 millisecond, your DSP chip will be running this 4096 FFT for 14 times. Okay, so even if you write FFT, which takes 100 microseconds, the 14 FFTs will be taking 1400 microseconds, which is equivalent to 1.4 milliseconds. But if you look at your time budget, you have time budget of 1 millisecond here. Okay, and in 1 millisecond, you are supposed to do the whole processing starting from FFT to CRC check. Even more than that, because you have some RF part, which is I'm not talking about. This should also be done. Okay, I'm skipping that right now. Only talking about what the DSP chip is doing here. Okay, so if you forget about these modules, and let's say all the remaining modules, let's say these modules take 800 microseconds. So out of 1 millisecond, the budget that you have for FFT is 200 microseconds. If you assume that the whole processing is 1 millisecond. Am I too fast? Just give me some feedback. It's like, are you able to see everything, or it's like too messy? Hello. Can some of you just give me some feedback? If you can see it, or if you're going okay, or am I too fast?
Yeah, they are writing in chat window that it is okay.
I can't see the chat window. So if you have some feedback or question, just unmute yourself and just tell me.
Okay, sir. Okay.
Okay, this is okay, right? We are going
Yeah.
with, it's not too fast. Okay. Okay, so if you look at here, you had 200 microseconds to run 14 FFTs of size 4096. Okay, that's so one 4096 FFT, you have this much time, which is too less. Okay, which is almost like around 15 to 20 microseconds. Okay, so the question is, can you write a 4096 FFT? Can you write a C code which can run the 4096 FFT in 15 to 20 microsecond or maybe faster than that? Okay, that's the goal. Okay, if you cannot write FFT in this much time, okay, it's useless. You can't run the chip. Okay, your code is useless. That's uh, I mean, until unless your code is faster than this, your algorithm or the work that you do is not useful. Okay, that cannot go into the hardware. That hardware even cannot process the signal. Okay, so so the thing is, this case, this particular example is not just applicable to just 4G or 5G. The same thing happens for other wireless technologies and other like image processing, the continuous signal processing. It's applicable everywhere. Like even like you have a mic, you're speaking. There's a chip sitting there which filters your voice. It just fine tune your voice in the real time. See, you're talking, I'm talking, and you're listening. So there's a chip which is just fine tuning your voice, changing the amplitude, or it's removing the noise. It's doing lot many things. Okay, and everything is happening in real time. There's no delay here. Okay, so so and everything the whole result comes from the optimization, like how fast you can run a code. It boils down to that. Okay, so that's like the one of the most important skill you must have. Then now we'll go to the code and we'll see how we can think of optimizing it. Let me, you can see this window, right? So what I did was I picked some of your codes from your second assignment, and will go over them one by one, and we'll see what are the different things that you can do. I had only one file, common functions. So this belongs to one of you. So are the text fine? Is the font size okay? Can you see it? Or should I increase the font size?
Yes, sir. We can see.
Okay, now fine. Okay, so this first function is, we look at it, this is convolution, and since all of you have written this function, so you must be knowing how actually the convolution works. So you basically have two for loops, and you all of you must have done this, and you multiply x with h and store the output in y, right? And x will be multiplied with all h, and each h will be multiplied with all x. So you have, so for that reason you have two for loops. Okay, now this, what this function does is, it has one input, one array, x int array. It has another array, h input array, one the length of x, the length of h, and the output array y. Okay, so you might be calling. So let's consider a problem where you are just writing a convolution, and that convolution, this particular function, might be used n number of times. So you have some application where you are just convolving two signals or a signal x with h, but continuously or like with like infinite number of times. Okay, now the task is to write this convolution function in a very optimized way, in a way that this runs as fast as you can write. Okay, now the first thing that you write it, you go here, you see, okay, you need two arrays. How do you think about it? So you need two memory locations, okay, which has length, okay, here the length of x plus the length of h minus 1, okay, and you initialize two new arrays with uh, this much size, which is x plus h, And then you, in the X array, you copy the input X. In the Y array, in the H array, you copy the input H, okay? And the remainings are 0, okay? So these are two things. So we'll go one by one. Let's target this thing first. What's happening? So let's say I have a function. Let's assume that I have a function here, main function or some other function. Let's say I have some real-time code which does filtering in the real time. Okay. And the job of this filter is it does a lot many other things, but one of the tasks is it calls this convolution function like 1,000 times, and it calls it with this inputs. Okay, I'll just remove this. So this is the normal code that you have. Okay, like you have a convolution function, you will be calling it. You may call it just once, that's okay, but normally you call it for a real DSP, you'll be calling it many times. Okay, so that's how you do. Now look at this problem. Let's say I put a for loop also. I'll be putting a dummy loop. Let's say I'll be calling it, let's say 10,000 times. Okay, fine. Now what's happening here? So every time I call a function, I come here, I call this guy. This function is defined here. So my loop will come here. It will first calculate the length, which is x plus h. It will then allocate some memory for x and h. Okay. Now we'll think of how to. Now the first thing is, do I need this memory allocation here? Okay. Because right now what's happening is every time I call a convolution function, which I'm calling 10,000 times here, every time I'm allocating some memory. Okay, so what if I allocate it only once and just keep using it? What if I just copy them from here? What if I just put them as a global parameter and I just keep them there? Okay. Now what will happen? Every time I will call a convolution function, it will come here. And I have the memory allocation done already. That's only one time. And this is the compilation time. So the compiler, if you have the global parameters, the memory allocation is done already. At the runtime, there is no memory allocation. So you will be just running it. So every time you run convolution function, you are not allocating extra memory. So you are not spending time at allocating some memory there. But now the problem is you don't know this y length. Okay, and y length is given at the runtime. Okay, which comes from xlen, hlen, this two, and it can be different every time. It can be different. So let's say the x length can be like, it can be from 10 to 10,000. Hlen also can be, let's say 5 to 500. The values can be anything. Okay, so what exactly we do in that case is we find out the maximum possible allocation for YH. So let's say in this particular case, I know that my max x length, it can be 10 also. Max x length will be 10,000. Okay, I know this already. I know my application. I know what exactly I will be doing in the convolution. What exactly my filter is doing. So I know the maximum length already. Okay, and I also know that my h length is 500. Okay, this is something already known. Okay, so what I will do is I will pre-calculate the maximum length, which is 10,500, and I'll just feed it here. 10,500. Okay, so one is okay, you can ignore it for time being. We'll just to look just to make sure that the number looks nice, we'll just keep it 10,500. So now we know the maximum allocation here. So when you do this maximum memory allocation, you are not optimizing the memory here. Okay, you are optimizing the speed. Okay, But when we write a code, we always take care of the worst case. What is the worst case memory allocation? And you always keep that much memory. Okay. And if you look at the current processors and the systems, even if your laptop, we are not bounded by memory nowadays. Okay, there used to be a case like maybe 5-10 years back, then the memory where the memory optimization used to be there. Like you will have to, you're supposed to focus on how much memory you're consuming while running the code. But now if you look at your system, you have 2 GB RAM, 4 GB RAM, 16 GB RAM or 32 GB RAM. On some of the servers, they have 64 GB on 512 GB RAM. So you basically don't care about the memory. You care about the speed because that's what you need for the current applications that you have. You target as fast as you can run. And so you always care about the worst case, that in the worst case, how much memory I will be needing. So in this case, I'll be needing 10,500. So I just fixed it. Other way to just write it that if you want to, let's say some other time you want to change it to, let's say 5,500. So you can define a macro for that, something like this, and you just keep it 10,000. This is a nice way to write a code. And what you can do is you can just write 500 here, and these guys you can put them in the header file. So you can do this. So this memory will be allocated at the compilation time, and you can always keep these guys here. Okay, now, so we are done with these 3 lines. So, okay, what exactly happening there? If you look at the code, you are running your for loop 10,000 times. So 10,000 times you are running this line and the other 2 lines which were there previously. Okay. Now 10,000 times you are doing some additional plus, adding to operation, to variables, and subtracting -1 there. It may not, it may take just 1 nanosecond, but if you do the same thing for 10,000 times, the time consumed by this particular operation can be huge. Okay. So what I just did was I allocated some memory and I just removed it. Now, but we still need yn because we need it for other operation. We'll keep it here. Now let's go to what's happening after that. Now what we are doing is we are copying x in to x because the x array that we allocated has bigger length. We need a bigger size array to store because for the convolution, that's how we are doing it. Okay, so what we are doing here is we take we copy them one by one. Okay, and the remaining values we just keep them 0. Okay, and we copy till x length. Okay, now the question that we should ask here to ourselves is, can I do better here? Can I write a piece of code which can run faster than this code? So how do you look at this algorithm? Can one of you tell me if you have any better way to do the same thing from line number 25 to 32? Okay, so how do you actually look at a particular algorithm? You call it a module which just copy x length data to another memory location and also 0 the remaining ones. Okay, so in this algorithm, if you look at, I initialize a new variable I with 0. That's one time. You do it only once for a single convolution. You do I is equal to x length -1. You compare your variable I with x length. Okay, and this comparison happens x length times. So if your x length is 10,000, you are comparing I with x length 10,000 times. Okay, so when you write an algorithm, you think about which operation take less time. Okay, So it's like when you become a good programmer, you should have a comparison between, okay, how much time, how many cycles my CPU takes to do a single addition, adding two 8 bits, adding to 16 bits, adding to 32 bits, adding to 64 bits, and how much time it takes to multiply two numbers if the numbers are 32-bit, if they are 64 bits, or if they are float or they are double, how much time my processor takes to do a square root or do division. You should have a rough idea. If you don't know how many cycles it takes, you should at least have some understanding of the comparison. Like, okay, if I do multiplication and addition, which one runs faster and how much faster? And if I do division and multiplication, which one runs faster? So you should have some comparison in mind before you write the code. So if you look at here, what exactly you do, if you are understanding this algorithm from an optimization perspective, you see, okay, my initialization is happening only once. Okay, that's totally okay. My comparison happening 10,000 times. Every time I'm increasing, so increment happens 10,000 times. I'm copying one by one. I'm copying 10,000 elements. It's okay. And for the remaining 500, I'm running again a loop which runs from x length to y length minus 1, which is, so 500 times I'm comparing I, and 500 times I'm incrementing it, and 500 times I'm going to that memory location and writing 0. So now the question comes, can I do better? Can I write a code which runs faster than that? Okay, now you can think about what exactly I'm doing here. I'm copying data from one memory location to another. Okay, so basically, if I explain this particular line, the first for loop, what it is doing is copying 10,000. So let's say my X array is float, okay, 4 bytes. So I'm copying 4 into 10,000 bytes from memory location 1 to some memory location, some other memory location. That's exactly what I'm doing. Now, do I have any better way to copy the same thing? Okay, can I just use a pointer? Or if I want a different memory location, like in this case, can I have an optimized way to do this? Okay, okay, let's say we have one. We can do it using memcopy. So there is a function already given, which is almost like 100 or 200 times faster than your for loop. So if I do simple memcopy here, I can do the same thing. I can just copy output in X array, so this memory location, and how much I'm supposed to copy. I'm copying this much. Okay. So if you compare these two, so if I give you a rough idea about the difference between the for loop that you have written here and the line I wrote here. So if your code is taking, let's say 300 microseconds, then my mem copy will take 1 microseconds. So that's the difference between these two. That's that much faster my mem copy is. Okay, so now I know that. Okay, so before you write this, you should know about different ways to optimize. So like one of them is, you should have a basic understanding what are the functions available which runs faster, which are already there. Oh, okay, so I did this. Now I can just remove this. Okay, now the second question comes. I have another for loop. I need to optimize it. What exactly it is doing? It is just putting zeros. So I have another function here which can just set either 0 to 5, whatever it is, which is memset. And so I'm not caring about the syntax here. I'm just talking about the different ways to optimize. So memset, I'm setting it to 0. And how many memory locations I'm setting? Okay, so this won't be x length. This will be actually x length here. So 4 into x length. It won't be 10,000. And here memset will be 0. And how many zeros? So the location here won't be X array. The location will be X array plus X length. You have a complete memory location of this 10,000, but the first 4 into X length you copied here. So the remaining 500, you are supposed to make them 0. So the memser takes a memory address, the starting address in the memory, which you want to, from where you want to start with. So what this function will do is, it will start from this particular memory location. Okay, it will set zeros, and for how many, for how much memory, how many bytes, okay, which is y length minus x length. And since it is a float, you can multiply with 4, since it's 4 byte long. Okay, so don't look at the syntax and all. Like, we're just talking about the algo here. Okay, so now you know the task that you're doing here. You are doing in almost 300-400 microseconds, which you can do just in 1 or 1.5 microseconds. So that's like 200-400 times faster. Okay, so now we are done with this. Okay, same thing here. We are just copying h. Same thing can be done for h here. Okay, we'll skip it. But let's say we have done this also. We used mem copy and all or different ways to optimize that loop. Okay, instead of x, you can just put h, or I will just leave it here. I'll just leave it here. Now, okay, the second operation, the next thing that we have is that the main convolution here, okay, which is you run a for loop. So if you look at this algorithm, you look at it line by line, what do you see is first operation is I'm declaring a new variable I initialize it with 0. I compare it with y length every time I increment it. Okay, so my increment happens y length times. So for this case, my y length is 10,500. I do it 10,500 times, and every time I check it, every time I make y array I is 0. Okay, so this internal loop, this particular line number 39, it gets executed these many times. Then I have one more variable, which is j, initialize is 0. I compare it with I increment it, and this thing happens. I don't know, this you'll have to calculate using some formula. So it's from 0 to I, and I is changing from 0 to y length. So this will be, so this comparison and this increment will happen maybe 1 lakh or maybe more than that times. Then what exactly you do? You multiply these two numbers, float values, store them in y. Now let's start here. Okay. First thing is, can I remove this y array I? Can I just set it 0 also? Can I do the same thing? What, like I know I already know some algorithm which can set a particular array to 0 in a very less time. So can I use the same thing just once? I just have y array. I keep it here. Okay, actually this is strong. This is okay, I guess. I set it 0 and I set it for y length times. So this, now I don't need this line. Okay, I'm done. So now the question comes, can I optimize this internal for loop? Okay, now you stuck here because now the multiplication should happen. There is no way. and basically we have no idea how to optimize this particular operation. Okay, so I will tell you some ways, some advanced algorithms to do these kind of operations. I won't discuss them in detail. We'll just give you a very high level understanding that in some of the CPUs, mainly the Intel and AMD CPUs, you can do multiple additions, subtractions, and divisions, and lot many, like some square root, square, or lot many similar things uh, at a time. And how many at a time? Like 8 at a time, 4 at a time, depending on the size of X array, or depending on the size of your variable. So I will just brief you about that. So maybe in the future, if you encounter, you may just apply that. So what happens in is these operations are basically known as SIMD, single, what is that? Single instruction, multiple data. Okay, these are supported by most of the x86 CPUs. Okay, what you do here is what this particular operation will do. Let's say in memory you have this address A, this variable A, this variable B. Okay, so let's say A is int A of size 8 and B also size 8. Okay, normally if you want to add A and B, what you do is, let's say you want to store in C, what you do is you put a for loop, I is equal to 0 to 7, Ci is equal to AI plus Bi. That's how you do it. Okay, and if you look at this case, what exactly it is doing, it initializes I to 0 once. It does this comparison, I less than equal to I less than 8 times, I plus plus 8 times, and 8 times it will do this operation. So there are some instructions which exist, which are known as SIMD instructions. What they do is they load this A and B into a memory location. So each one is 4 byte. So the size of A is 256. Is it 256? 256 is the byte or the 256 bits. Okay. So what these SIMD do is, so in your CPUs, you have some big registers. Okay, you might have known these registers from your computer organization course and other courses. So what they do is you load this A from A0 to A7 in this memory address. So this goes from A0, A1 to A7. And you also load B0 to B7. Okay, these are two registers. They are, maybe you can Google them later, and these registers will be directly added. Okay, in a single cycle, in a single instruction. That's what it is. Single instruction, multiple data. So you have multiple data and a single instruction, and in a single CPU cycle, A and B will be added. So your code will be 8 times faster, not just 8, maybe more, compared to this code, where you are running it 8 times. You will run the CPU will execute this in single cycle. Okay, and there are different such registers. They are known as XMM, ZMM, kind of. You can just remember these names later on if you come across. And the current Intel CPUs, they support till 512. Okay, these are called intrinsic. basically you do the parallel processing. Okay, so here what matters is, so let's say the integer here a is size of 4 byte, but if you take, let's say, a character which is 1 byte, okay, instead of 8 you can pick 32, right? So 32, where your for loop was taking 32 cycles to do addition, here you can do the same thing in a single cycle. Okay, so these are some advanced optimization ways, not so advanced, which can be applied here. There are some simple ways to apply. Okay, and not like you'll have to copy. The one way is you manually copy into registers and then do the addition. Other ways you can use some simple compilation flags and pragmas to optimize similar things. We won't discuss those things here. Okay, now we'll move to the next function. So now let's see what's happening here. Maybe we'll discuss the upsampling part. Okay. Now let's understand this. So in the upsampling, what we are supposed to do is, you are supposed to copy the alternative samples, and how many samples is depends on the upsampling factor, which is n, I guess, yeah, n here. So n decides how many samples I'm copying. That's it's nothing but the copying the samples, right? Let's a simple case assume n is equal to 2 here. X length is equal to, let's say, 1000, and u length. Okay, u length is not given. Let's assume something. It's equal to 2000 since n is 1000. N is 2, so okay. So now what I'm doing is I'm copying X length data to, sorry, data from X in array to U array and copying to the alternative locations. Okay. Here in this case, since n is 2, so how this particular code is written, you have I is equal to 0 one time. You compare it with X length into n, which is 2000. So this for loop is running 2000 times. So if you look at, there are 2000 comparisons, 2000 additions, and a single initialization. Okay. Now, if you look at here, 2000 times I'm executing if condition. If conditions are not so simple, they are costly. Okay, so you try to minimize the if conditions if you can, because it's not like if conditions are executed in a single cycle, they are costly. And here you are running the if conditions 2000 times. Every time you take the percentage and you also compare. So if you see, there are what exactly you are doing is, every time you check the remainder, and every time you compare it to 0. Okay, and if it is okay, then you execute this particular operation, which in this case runs 1000 times. If there's else condition, and this also goes 1000 times. Now, since we have already discussed some better ways to do similar operations, maybe you can yourself think of what are the ways you can reduce these operations. So first thing you think of is, let's say I'm running 2000 times, I'm checking every sample. Can I remove this if condition? Do I really need to check this thing? Do I really need to check whether my I is divisible by n or not? Is there any better way? Can I do it in some other way? Can I just modify my for loop? Can I just modify my increment condition to some other condition where I'm just jumping one after the other in the memory? And other thing is, do I really need to make it 0 every time? Like, okay, this we already know, else case. So I'm just in a very straightforward way, I'm just removing it. And instead of that, since we already know here, that memset works 100 times faster, I can just copy it. So even before running the for loop, I can just initialize it 0. I can just initialize the whole memory because this is like, this runs in like nanoseconds. So this output array, I can initialize, and how much I'm supposed to initialize? You can initialize to either the maximum memory or to x length into n into 4. This much. Or instead of 4, if you don't know the size, you can just write size of float. That's what you can do. Now, since I have already done this, I don't need an else condition here because that's consuming some CPU cycles. Okay, now coming to the lines 71 and 74, can I combine these two lines and make a single operation? Okay, so now what if I just do I is equal to I plus n? Okay, and if I remove this, okay, now I have to adjust something here. I don't think so. I think, is it okay now? I think so. I is equal to 0, this is 0, this is 0, I is equal to 2. So this will be 1 and this will be 2. Okay, this is fine. Now, okay, what we have just done is we have removed 2000 if conditions, and not just 2000 if conditions, 2000 checking that I%n and 2000 comparisons comparing with 0 whether they are equal to 0 or not. So basically 4000 operations you have just removed from this unnecessary if condition. Okay, now the question comes, can I do better? Can I remove this for loop, or can I just do something with this I divided by n, or can I just do something with this whole for loop, or can I just replace this with some optimized algorithm? Okay, now look at this, what's happening. This executed only once. This condition check happens in this case 2000 times. I increment it every time, incrementing 1000 times. And one more thing I'm doing here is that division. Every time I'm dividing I by n. So one thing that you must know, that division is the most costliest thing to do compared to the remaining four, the addition, subtraction, multiplication, and division. Out of all four, division is the most costly thing. So if you remember your BTech or MTech courses, how exactly your CPU divide to run numbers. So if you might like, you represent these numbers in the binary and you do a binary division. And in the division, how many additions, operations, shift operations are there? There are a lot many. Division is the one of the most costliest thing. So one thing you do is you try to convert the division into multiplication if it is possible. So like for one case, it's just in a simple example. Let's say you have this some operation where you are supposed to divide the x in by 2 and assign it to u array. Now, you know that division is costly. Can you convert this into multiplication? Of course, you can convert. Instead of dividing by 2, you can multiply with 0.5. And this multiplication will be faster than that divide by 2. Okay. Now the question comes, can you do better? Do you have any other algorithm which runs faster than this multiplication? Yes, there is. So if you know, the shift operations are faster than the divisions and multiplications. Okay, so instead of dividing by 2, can you just do a right shift by 1? Okay, right shifting by 1 is nothing but dividing by 2. So if your division and multiplication are in 2's power, you can just simply use the shift operations for the division and multiplication because they are much faster. So since here, if you already know that my n will always be in 2's power, it will be either 2, 4, 6, 2, 4, 8, 16 kind of, then instead of dividing here also you can do shift operations. But if n is not multiple of that, you try avoiding it. Okay, so basically it's n minus 1 if n is 2. Okay. Now still we have a question. So if you are optimizing a code, every time you ask yourself is, can I do better? Can I do better than this current algorithm? Can I just remove the whole for loop and put something else which works faster than this? Yes, there exist. There exist multiple ways to do this. Okay, but they are not so straightforward. Maybe you can think of something, but one way is to using the inbuilt instructions which are CPU specific. Okay, I won't talk about much detail about those instructions. The same there is CPU specific for Intel, AMD, for x86, or for EIDSP. They are specific to that, where you can group multiple data and do this operation. I will remove the last one. You can process multiple data in a single cycle. You can do the whole thing. Like if this thing is happening at 2000 times, that operation, that single instruction multiple data operation will happen 2000 divided by 8 times, or 16, or 16 or 32, whatever it is, depending upon the how many data you are processing in one go and what is your variable size. Okay. Now maybe we have half an hour. Maybe I will talk about something else. So this will give you a basic idea that for every single line that you're writing, how can you think of optimizing it? So if you know that you are running a particular function many times, like you're running 10,000 times, if some operation which you can put outside the function, you always try to do that, like a memory allocation here, because when you write the convolution here, you don't think of running it only once. You're running it 10,000 times or maybe million times here, right? So you always try to see, do I need this particular operation here? Do I need it, or can I put it outside? Can I just do it outside and just store it? Okay, like for an example, I'll give a few more things here to think of. Let's say here what you are doing is y array equal to square root 2 multiplied, you are just dividing this itself. Okay, this I'll just copy here. Okay, so what you have some operation and you are supposed to do this. You are just supposed to multiply square root of 2 to this before you give the output back. So before you give the output back, you are supposed to do this particular task. Okay, so what exactly you can do here? If you look at this particular thing, how many times you are running it? You are running it in yi length and this I, so it's like maybe almost 1 lakh times. 1 lakh times you are calculating the square root, and you know calculating the square root is not easy. Maybe you remember the square root of 2, but for a CPU, calculating the square root is not at all easy. It takes lot many cycles to calculate a square root. Okay, But since you know this is a fixed number, what you can do is you can put a macro here so that you help your CPU don't to not to calculate the square root. What you can do is you can just write the square root. Sorry, I will put define square root of 2, and I know that it's 1.4141, something like this. So I pre-calculated this. It's a fixed number, and I'll just keep it here. That's it. So my CPU is not calculating square root of 2 now. It's a pre-calculated value. You can keep these kind of things in your header file, and you can use them wherever you want. Okay. So when you are optimizing a code, you think about every single cycle, every single operation, how many times I'm executing. Okay. Is it?
Means the line 17.
Here. So what is the question? Can we initialize this as float?
Float X array of this equals to curly bracket inside 0.
No. So okay. So there are two things here. One is declaring a variable and defining a variable. Okay. There are two things that you should know, and you should know the difference between these two. Declaring a variable, and the other thing is, okay, this is not the comment. This is defining a variable. Both of them are very different. So I will talk about particularly for C programming. Okay, declaring a variable means you just name a variable, you define the type of it, okay, size of it. Like for X array, what do I mean declaring means? Let's say int, I'll just write here int, that's a variable A, and let's say size 500. Okay. Declaring means you tell your compiler what is the type of this variable. It is of type int, and you also tell what is the size of that variable. The size is 500. So the actual size becomes in bytes 500 multiplied 4. So these many bytes. So you declared it. When you define it, you allocate memory for it. Okay. So in this case, this is called the definition. Okay. But what happens with the C programming is your compiler do the definition and declaration at the same time. So if you write a variable like this, int a 500, okay, it has defined it and also declared it. Okay, so if you check, if you print the value of this, there will be zeros. So your compiler by default defining means it has allocated some memory for this A. So some memory which is of size 500 multiplied 4, which is 2000 bytes. So your compiler have already allocated memory. Okay. In C, compiler does the declaration and definition in one go. So you are not supposed to write this. I mean, if you write, it's okay, but the compiler does both the things in one go. Okay, but not always. And this may not be the good way to write a good code. Maybe if you are a very good programmer, you are, and your variables are shared across multiple files, you always try to do that. So, okay, I will write a syntax where your compiler only declare a variable, it does not define it, which is extern and a 500. What happens here? This particular line won't allocate the memory address for A. It will just tell the compiler that A is of type N and head size 500. Okay, so if you try to use A before defining it, your compiler will throw an error. or it will because there is no memory for it. It doesn't know where exactly A exists. Okay, compiler should know in the memory what is the memory address from where I should pick A. Let's say if you try to print A10, you try to print it. Okay, your compiler will say that I don't know where exactly A10. I don't even know what is the memory address of A. What is the starting address? It cannot print it. It will throw an error because this guy did not initialize, did not even define the memory also. But in this case, if you define a variable like this, and if you print A10, it will just print some value because it knows what is the address. So if you are using extern, it is used when when you are sharing variables across multiple files, then you always do int a 500 is equal to 0 or some other value, not just 0. You always define it. So these two things goes hand in hand. If you are using A here, you should always put some memory. You need not to do this. It's okay even if you just write it. Okay. So memory address for these two, it's same now. Both points to the same location. Both are same variable, of course. Okay, and this guy, so normally what we do is we define this guy in the header file. So this declaration happens in the header file, and this memory location happens in some other file, some other .c file. Okay, so that's the difference. But this guy can go into either the header file, either header or .c file. It can go in any of them. Okay, so you should know the difference between these two. Okay, do you have any other question
One
before we
question.
move to something else?
Yeah, one question.
Okay, let me first explain it, what exactly I'm trying to do. Okay, so I have a matrix A. This is the matrix. Okay, let's say M cross N. I have another matrix B. Okay, this is also M cross N. I am doing pointwise multiplication, means A11, B11. I am multiplying A11 with B11, A12 with B12. Similarly, AMN with BMN. Okay, I store them into C11, C2, CMN. So C is also of size M cross N. This is a simple task I am trying to achieve here. Okay, in the code. So what exactly we do sometimes? You pick A11, B11, multiply and store somewhere in the C11. So this is your output matrix. Okay, you multiply A11, B11, store them into C11. Next time you pick A12, B12, multiply these two guys, store them C12. Or it's up to you. You can go in any way. You can multiply these guys first, then these guys, then these guys, or maybe you can move this direction, in this direction. It's totally up to you. So your target is to just multiply both the matrix one by one, element wise, and store in C. There are two different ways. Both are very simple. I try to write them here. So I will explain you the code line by line. A, B, and C, three matrix. P, Q, R, again three matrix. For simplicity, both are same size. So all of them are same size. Okay, I initialized all of them with some 2. That's okay. You can initialize with anything. It's totally fine. Okay, and this is the main code. Look at this code very carefully. This is method 1. I will write here. Method 1. Okay, and so this outer loop here, it is just for profiling. So you ignore it. This code is for profiling. So this is the main code for the multiplication. And like we normally do, what do we do? You go 0 to n, index 1, index 2, 0 to n. You multiply a, b, write the output in C. Like very simple, isn't it? I mean, that's the way, that's how we have been doing it, okay? And there is another method here. Both look same. There is no difference. Maybe some of you can't even observe there is a difference here. Okay, this is, again, you can ignore this. This is for profiling to check how much time this code is taking. And you run index 1 and index 2 and I just flip the index. Earlier, index 1 in all three, index 1 was first, index 2 was second index. Here, index 2 came first, index 1 came later. So if you explain this in the method 1, I'm going row wise. Okay, first I multiply first row with first row, second row with second row. Okay, rows. In the method 2, I'm multiplying columns. So I pick first column, then multiply with the first column, second column, multiply with the second column, right? And at the end, output is same. Okay, output should be same. Now, can some of you tell me which one will run faster? And okay, whether one of them will run faster or they both will run in the same time? First question. And if one of them runs faster, then which one and why? Can you just spend 2-3 minutes and tell me, is there any difference here in terms of the profiling, the time your code is taking? So maybe better I just look at the code. This is method 1. This is method 2. Look at this code very carefully, spend 2-3 minutes and tell me if you have any idea. Just say something. If you have any idea.
Depends on the value of m and n.
Sorry?
Hello, sir.
Yeah, tell me. Yeah, I could not hear you. Can you please
It
repeat?
depends on the value of m and n.
No, there is only n here, the size n. If you look at
Is the matrix square m by?
this is a matrix. And anyway, if you look at the here, the number of multiplications are same. Okay, the number of multiplications are same. They are m cross n. So even if you have different size matrix, it doesn't matter. So here you are, since it's element wise, this guy is with this part is with this, it's element wise. So the number of multiplications are exactly same. And for this case, the size of both, it's a square matrix, it's n cross n. So in both the methods, if you look at the for loop, the number of multiplications here, they're exactly same. Both the for loops are running same number of times. This guy is running 500 multiplied 500. If you look at n is 500 here. Both are exactly same. There's no difference. The only difference is the index is flipped. Here index 1 is first, index 2 is last. Here index 2 is first and index 1 is last. That's the only difference in this code. Okay, let me, since we have only 10 minutes left, let me show you. Let me compile this code. Okay, this is C01 variable size. That's, okay, one more file is there. I compiled it and I will be running the executable. Since I'm running it for 10,000 iterations and the matrix size is huge, it will take some time. Okay, I will run it with, so here if you see, but I don't believe the results. I will run it with, maybe to run it faster, I will just run it with optimization flag 3 so that we can quickly get multiple results. Okay, my system is, oh, sorry. My O3 flag is wrong. I will briefly explain you about the optimization flags. So look at the results. I will run it again. My system is 2.2 gigahertz. So if you see, my second method is taking double time compared to the first one. Right now, your question is how? It's like you don't even care how you are putting the indexes, right? When you normally write a simple multiplication. But even though the number of multiplications are exactly same, there is no difference in the code. Still, your second method is taking double time. Double is huge, right? If the first one is, if not, like if it is a 500, currently it's a 500 cross 500 matrix. But if you have, let's say, 1,000 cross 1,000 or 10,000 cross 10,000, this number can go like your CPU can take infinite time just continuously calculating it. And let me just flip one of them. Let's say I'll keep the number of multiplication same. Let's say I keep this first indexing same, index 1, index 2, but let's keep the last one different. Let's try it again. Oh, it's 4 times. Almost 4 times. Again, we'll see one more time, just to make sure that the results are, I mean, we are actually looking at the comparative results. So if you see, my second loop is taking huge time compared to the first one. Okay. Now, where exactly I'm going wrong? Even though, like, whatever we have discussed so far, we used to take care of the operations. Here, the operations like the comparison, increment, this comparison and increment, they are exactly same in both the methods. The number of multiplications are exactly same, which are nothing but 500 cross 500 multiplications, which are 25. Okay, one more zero. Okay, fine. But still, my method 2 is 4 times costly. That's huge. That's a huge difference. Okay, now I'll tell you something which I'll just brief you about the memory access that your CPU does. Okay, how exactly your CPU process the data? You know some basics. Okay, I'll just go very quick. This is your CPU. Normally you have cache 1, cache 2, main memory, mainly RAM. You have cache 3 also. Okay, and then RAM. But okay, for this example, let's have just cache 1, cache 2. Okay, we all know cache 1 is very close. Oh, something happened. We all know that cache 1 is very close to CPU. Okay, and very fast. So the speed, the link that you have between CPU and this, it depends on how far your memory is sitting. Okay, so this guy is very fast, this guy is, this access is slow, and this is very slow. And if it is hard disk, HDD or STD, it's very slow. The read write is very slow. So normally your data goes from RAM to cache 2, cache 2 to cache 1, cache 1 to CPU registers. Okay, your CPU will do this addition A plus B or A multiply B, will write back. Okay, or maybe directly here. Okay, and the whole thing, which data is going from RAM to cache 2 or cache 1 or to registers, which data it is writing back to RAM or cache 1, totally depends on your algorithm. Okay, so your CPU works in a different way. It's not, so we'll take this example, we'll quickly finish it. Your matrix, this was your matrix of size n cross n. Let's take simple 4 cross 4. Okay, we'll take simple 4 cross 4, A11, A44. Okay, let's say one is 4 byte. Okay, so this total is 16 byte. 16 byte width and 16 byte depth. This is your memory address. Okay, if you look at the first method, you are picking first one, then this one, then this one, then this one. This was the order. Okay, and then you multiply with the different matrix. In the second method, you are picking this guy first. Maybe I will pick different color. This is, then this one, then this one, then this one. Then you are going to the second column. How your CPU actually does this? So when the very first time when you pick this data, A11, okay, you pick this data, then your CPU assume that the next memory also you are going to use. Okay, so it's not like, so A11 is just 4 byte. Okay, so which is currently sitting here in the RAM. Here your complete A, which is 4 cross 4 right now, which is sitting here in the RAM. Okay, now when your CPU is, when the CPU need A11, it will, that A11 will come all the way to registers for the multiplication. Okay, but the CPU thinks that you may need the next memory address as well. If for the memory you have 16 cross 16, 256 bytes, so they are always continuous in memory. Okay, the CPU, your CPU allocates them in the continuous memory allocation like this. Okay, so when you need this A11, CPU assumes that you may need the next memory address as well. So why don't I pick in chunk? CPU won't just pick A11 and give it to registers. What it will also do is, this guy will come, so it will pick 64 bytes or 120 bytes or 256 bytes in chunk, and it will copy them in cache 1. Okay, it will keep them here. Okay, so okay, for this case, what it might copy is, let's say it copies A11, A12, A13, A14. It will copy these 4 things from RAM to cache 1, and CPU will pick A11 because it currently needs A11. It will do the multiplication. It will write back A11, which will go all the way back to RAM where exactly it's there. It's wherever the memory address is, the C11, wherever the output you are writing. Okay. Now in the next iteration, next CPU cycle, I need A12 in the method 1. In the method 1, if you look, when I read A11, I'm reading A12. Okay. Now my CPU needs A12, but my A12 is not in RAM now. My A12 is in cache memory already. Okay. So I won't have to go all the way to RAM to pick A12, do the multiplication and write back. A12 is already there in the cache. I can directly pick it and just do the multiplication. That's very fast. Because let's take some number. Let's assume that reading from the RAM takes 100 nanoseconds, just a rough example, and reading from the cache memory, let's assume takes 10 nanoseconds. So when I read for the very first time, okay, it took 100 nanoseconds for A11, but for A12 it took just 10 nanoseconds. It's very fast. But in the second case, what happened? In the second method, method 2, instead of reading A12, I read A21. Now A21, so or you see that our matrix was very big, 500 cross 500. Okay, which is huge. So my CPU won't load this much data from RAM to cache 1. Like this is just 250 bytes. For a small matrix, it can just load everything. But for a big matrix, it won't load everything from RAM to cache 1 because my cache is the smallest memory. If you look at your cache memory size, it's very small. And not just the multiplication, my CPU is doing lot many things. Like in the current time when I'm writing this code, my CPU is running Google Meet or so many other things in the background. Okay, so all those other applications also need cache memory. So I can't just use the whole cache at the same time. My CPU will give just a chunk of cache for this particular multiplication, and I will be using that. Okay, so when I'm accessing A21, my A21, the memory address of A21 is 500 multiplied 4 memory address away. This is the length of this is 500, and each one is 4 bytes. So my memory address of A21 is 2000 bytes away. Okay, so now that's so obvious that my CPU won't load 2000 bytes from RAM to cache. Okay, so if I'm doing A21 in method 2, CPU will again go to RAM. It will pick A21. It will bring it to cache. Now again my CPU will think that, okay, I may need other memory address. So it will think that, okay, you may need this memory address A21, A22, A23, A24. So it will just pick everything from RAM, load it to cache, it will just use A21, and then it will write the output in cache 1, and again it will think, oh, I'm not going to A22 now. Sorry brother, I'm going to A31. Okay, so my whatever I loaded, it's useless now. Okay, now I will have to again go to RAM, pick the data, and it will happen every time. It will happen for all 500 cross 500 times. Every time I'm going to RAM, picking it. So think about it. It is just RAM. Think about what if you are loading data from hard disk, okay, which is far away, which takes in microseconds. Let's say one microsecond. And if you write a code, like normally when you work with image processing or machine learning where you have huge data, like you have data in gigabytes, 10 GB, 1 GB data. In that case, your CPU won't load everything into RAM. You will be accessing data from hard disk. Okay, they are written in some files. They are stored in hard disk. Every time you are reading them from hard disk to this way to CPU. Now, if you don't pick the data in the right way, and if you have 1 GB data reading from hard disk, a very good algorithm where the number of multiplications and divisions are same. Consider about two methods where both of them have same multiplications and divisions. One method can run in like 1 minute, and another method can take 1 day, whole day, because there's a huge difference. There's a 10 nanoseconds and there is 1 microseconds. It's 100 times. The difference can be as big as one whole day. You are just running the algorithm whole day, right? So when you write, so these are just like the very basic. I'm just putting to make you think when you write a code that it is not just about the operations. It's about how you are reading from the memory as well. Okay, so you can do. Okay, we will also briefly discuss about the optimization flag. So there are flags which you use with BCC or ICC, which are O0. So when you don't put any flag, your compiler runs with O0 flag, which is it is called optimization flag. So there are O0, O1, O2, and O3. O3 is the fastest one. So what does your compiler do when you put this flag? It will optimize the algorithm by itself by removing the unnecessary things and make your algorithm run fast. Okay, so okay, I will tell you like what even the O3 sometimes can go bad if you are not using. Let's say I will give you an example. I will just comment this part here. Okay, so what exactly I am doing now is I did the multiplications here stored in C and R, but I am not using C and R anywhere, right? In a short code, earlier I was writing both of them in a file. Now I'm not writing them anywhere. They're useless. I'm not using them anywhere. Okay, now I will be running this code. It takes 0 microseconds. How is it possible? If I'm running with flag O2, let's see, 0 microseconds. Where I was running with O0, the same thing was, okay, it will take some 600 microseconds and it will give the results in milliseconds. But did you look at the difference? If I run with optimization flag 3, look at this, it's 1200 microseconds, almost 1.2 milliseconds. And this guy is 0. What exactly happened here? Your code did not run. Look at the code. What exactly your O3 flag did here? It did not even do these operations. It did nothing. It came here. What O3 flag does is, your compiler try to see what is useful, what is not useful. That's one of the things it does with O3 flag. Okay, it came here, it checked everything. Okay, A, B, some memory allocation, some memory setting. Okay, some multiplication happening. It will check everything. Okay, P, Qs. Okay, I'm writing output in R. Now it will see, okay, I'm not using anything. So why do I do this? Why do I do all this? It won't do anything. It will just do nothing. It will just exit. Okay, if you print R, then okay, it will be like, okay, I'm printing R, so I'm using R somewhere. Okay, then okay, I will have to calculate R. Otherwise, it won't even do the calculation. It will just don't do anything. It's very useful. You should always compile your code with O3 flag, but you should also take care whether you're using the variables or not, or whether you're changing them or not. What O3 may sometimes does is, if you're not changing the parameters, it will automatically keep the variables in the cache. What it will also do is, so let's say there is some variable, you are not changing it and you are keep using that variable again and again. So it will keep that variable in the cache memory all the time until you drop it. Okay. So that's also one of the thing O3 flag does. And there are many other things it does, but we don't have time. Maybe